Have you ever wondered how geologists find valuable mineral deposits hidden deep within the earth? It's not just about luck or a pickaxe anymore. Today, it's a high-tech science, combining powerful instruments with sophisticated math. Let us dive into the fascinating world of geochemical data analysis and discover how scientists turn simple rock samples into treasure maps. Reliable geochemical interpretation hinges on two main pillars. First, advanced analytical technology that gives us high-quality, specific raw data. And second, specialized statistical methods that correctly handle the data's complexities. It's this powerful combination that allows us to extract unbiased, accurate insights. Let's start with the first pillar, the incredible analytical techniques. Over the years, our instruments have become incredibly precise. This allows us to use what's called high-precision lithogeochemical data in both research and mineral exploration. These advanced techniques are sensitive enough to capture tiny details about trace elements and isotopic signatures, which are crucial for understanding how ore deposits form and where to find them. One of the workhorses in this field is high-sensitivity multi-element analysis. Modern instruments can now routinely analyze a huge range of elements at extremely low concentrations. This helps us spot very subtle anomalies that could point to a hidden deposit and establish what the normal background chemistry looks like. A star player here is inductively coupled plasma mass spectrometry, or ICP-MS. This technique is a favorite because it has incredibly low detection limits for nearly every element on the periodic table. It's perfect for what we call ultratrace element analysis, looking for things like rare earth elements, thorium and uranium. ICP-MS can detect elements down to sub-parts per billion levels, giving us a rapid, multi-element snapshot of a sample's chemistry. But with great power comes great responsibility. As our analytical techniques get more sensitive and detection limits drop, we have to be extremely careful about contamination. Even a tiny amount of contamination can create false anomalies and lead to completely wrong conclusions. So, clean labs and careful procedures are absolutely essential. Beyond just what elements are present, we also need to know where they are. This is where high-resolution spatial and isotopic analysis comes in. These specialized techniques give us microscale and even time-related information, which is vital for a detailed interpretation of geological processes. A key method here is laser ablation ICP-MS or ICP-MS. Its real power is its ability to create spatial maps of elements and their ratios directly on solid samples, like individual mineral grains or even microscopic fluid inclusions trapped inside crystals. This microscale analysis allows us to reconstruct the history of geological fluids. For example, by analyzing trace elements like tin or antimony in sulfide minerals, we can piece together the hydrothermal evolution of a volcanogenic massive sulfide deposit. Another critical aspect is isotope ratio analysis. ICP-MS makes it possible to routinely measure natural isotopic ratios. Signatures from radiogenic isotopes like lead, neodymium, and strontium provide fundamental clues about the source of the metals and the tectonic environment where the magma is formed. For instance, analyzing lead isotopes is a common method used to help classify different types of gold deposits. So, we've gathered all this amazing, high-quality data. But what do we do with it? That brings us to our second pillar, specialized statistical methods. These methods ensure our interpretations are reliable by first checking the quality of the data itself and then applying advanced models that account for the unique nature of geochemical information. First up is quality assurance and quality control, or QA or QC. This is non-negotiable, especially in the mining industry where regulations like Canada's NI 43101 mandate it. A well-designed QA or QC program helps us spot errors and figure out where they happened. Was it during sampling, sample preparation, or in the lab instrument? To monitor accuracy, we use certified reference materials with known compositions and track the results with statistical tests and control charts. We also use blanks, which are samples with no expected minerals, to check for contamination. To monitor precision, we systematically insert duplicate samples at various stages and evaluate the results using various statistical plots and tests. However, geochemical data often doesn't follow a nice, normal bell curve distribution. This can be a problem for traditional methods like the Thomson-Howarth plot. A more robust method, especially for nuggety elements like gold, is the average coefficient of variation, which handles this non-normality much better. Now, let's talk about a major hurdle in geochemistry: compositional data. Geochemical data represents parts of a whole, meaning all the concentrations add up to a constant, like 100%. This creates a mathematical constraint that can cause standard statistical methods to produce misleading correlations. This is where compositional data analysis, or CODA, comes to the rescue. The core idea of CODA is that the important information isn't just in the absolute concentrations, but in the ratios between the elements. By using a mathematical trick called a Lagrange transformation, we can convert the constrained data into a format that standard statistics can handle correctly. The centered log ratio, or CLR transformation, is a common way to do this before running more complex analyzers. By using CODA, we eliminate those pesky spurious correlations and get a much truer picture of the relationships between elements. With our data cleaned, checked, and properly transformed, we can move on to advanced multivariate and spatial interpretation. Geochemical datasets are inherently multivariate, meaning we're dealing with dozens of elements at once. A simple outlier in one element might not be significant, but a combination of several slightly unusual values could be. This is where multivariate outlier detection, using methods like Mahalanobis distances, becomes powerful. It helps us identify samples that are truly different, often representing a separate geological process like mineralization, rather than just random noise. By using robust statistical estimates, we can make sure these outliers don't skew our main interpretation, which should focus on the dominant geological processes. To make sense of all these variables, we use a technique called factor analysis, a form of dimensionality reduction. A common method is principal component analysis, or PCA. PCA takes all our correlated elemental data and transforms it into a new set of uncorrelated variables called principal components. Each component represents a group of elements that behave similarly, which can often be linked to a specific geological process like alteration or mineralization. We can even use a staged approach to refine this and isolate a multi-element signature that is closely related to our target. But what about separating anomalies from the background? Many elements don't follow a normal distribution, which limits conventional methods. Here, we can turn to fractal theory. The concentration number multifractal model is a powerful tool for classifying data, like a map of our mineralization-related factor. It helps us separate truly anomalous regions from the background without needing to normalize the data first. Finally, the world of machine learning is revolutionizing how we create geochemical maps. Techniques like quantile regression forests can generate highly accurate and interpretable maps by integrating our geochemical data with other information, like geophysics or remote sensing data. This is a huge leap forward from older models based just on spatial correlation. And most importantly, these modern models can also produce maps that show us the uncertainty, telling us how confident we can be in the predictions for different areas. So, in the end, it's a synergistic process. Advanced analytical techniques give us the raw, high-resolution chemical data. Then, specialized statistical methods act as our interpretive lens. They validate, clean, and model this complex information, giving us a defendable and reliable basis for all our geological conclusions, whether we're exploring for new resources or assessing environmental impacts. Thanks for watching. If you found this journey into geochemical analysis interesting, don't forget to like, share, and subscribe for more deep dives into the science of our planet. See you next time.